Welcome you all to learn the GATE lecture video for linear algebra. I am Dr. Choudri, Associate Professor, Department of Mathematics working in SAEC Engineering College. In this video, we are going to learn basis, linear independent and linear dependent. These are the essential topic in linear algebra. See, basis and its dimension. Basis definition is a subset B of a vector space B over a field F is called a basis of B if B is linearly independent and B equal to L of B. That means B spans B. Dimension is nothing but what are the number of elements in a basis of a finite dimension vector space V of F is called its dimension and it is denoted as dimension B. Okay, so how we are going to understand the concept of basis? For best example, when you go to any function, that may be the marriage function or a college symposium or cultural whatever it is, there you will see the group of people gathered separately. Okay, some for example, if it is marriage function, bride and bridegroom. Okay, so some people are from bride relatives or bride friends, some people are come from bridegroom relative friends and etc. Okay, see, certain people are there, if they are relatives dependent. Suppose the gathered people maybe like friends, students and neighborhood and some other people are there, means that is independent. However, it is when we say that when we have to conduct the function in smooth way and successfully, when you call each and every people for our function, then only it will be successful. That's why the basis also, the set of elements are there, that should be linearly independent. If it is linearly dependent means when we call the relative people alone, that is like a family get together, not a function. Have you understood what I am telling now? See, basis of a vector space should be subset, then the elements are linearly independent, then that elements spans V. That is the concept of basis. Let us discuss what is vector space first. A vector space of V over a field F consists of a set on which two operations are defined. Okay, see, I am taking the two elements from V, x plus y. X comma y, there is a unique element x plus y belongs to V. Then scalar multiplication. I am taking the scalar from the field here and the element from V, then the combination A into x belongs to V. Full explanation. For all x comma y, I am taking two elements from V, x comma y. The operation should be x plus y or y plus x. Both are present in this vector field V. That is called a commutative under addition. Next, taking three elements x, y, z, then x plus y plus z or x plus y plus z. Both present in this vector V. Next, there is an element 0, that is called identity element 0 under addition. Here, for each vector x belongs to V, there is a unique vector minus x, that is called inverse element of x. Each and every elements of V has the inverse element under addition. Okay, then identity element in under multiplication, 1 into x equal to x. Okay, also associative property under multiplication, A into B into x equal to A, B into x. For all A comma B belongs to F, x belongs to B. Then distributive property under multiplication with addition, A into x plus y, that can be written as AX plus AY. Both are x's means then A plus B into x equal to AX plus BX. For all A comma B belongs to F and x belongs to B. Okay, so this is the definition for vector space. And subspace. A non-empty subset W of a vector space B over a field F is called a subspace of B if W is a vector space over F. The subset W itself vector space, that means the previous axioms should be hold. Under the operations of addition and scalar multiplication defined on V. Okay, the important points are 0 and V are the subspace of any vector space V and are called the trivial subspaces of V. Second, a non-empty subset W of a vector space V over a field F is a subspace of V if and only if for each pair of vector x comma y belongs to V, taking scalar from field x plus y belongs to W, Ax belongs to W. So out of the axioms, the subspace should be satisfied these two conditions must. Now we come to what is linearly independent and what is linearly dependent. Okay, so in this linear algebra, first we have seen the basis. Basis definition is over. Basis definitions, especially the subset and vector space, that the definition is also over. Now we come to the definition for linearly dependent and independent. The same vector space, when we take these vectors v1, v2, v3 up to vn, are called linearly dependent. Take a scalar from the f, alpha 1, alpha 2, alpha 3. That is called a linear combination of scalars and vectors. So alpha 1 into v1 plus alpha 2 into v2 plus alpha 3 into v3 up to what? Alpha n vn equal to 0. In this sum equal to 0. Maybe v1, v2, v3, vn are all non-zero elements. At least one element of this vector should be non-zero. So what is the chances are there? Alpha 1, alpha 2, alpha 3, alpha n maybe equal to 0. Here alpha 1, alpha 2, alpha 3, alpha n, out of these elements at least one alpha 1 or alpha 2 or alpha 3 up to alpha n not equal to 0, or all are not equal to 0. That is called a linearly dependent. Second case, the same linear combination, only one chance is there, equal to 0, when alpha 1 equal to 0, alpha 2 equal to 0, up to alpha n equal to 0. In this case alone, this linear combination equal to 0. Okay, both are based on linear combination only. Linear combinations are scalars from field F, vectors from vector space. This combination equal to 0. At least any one of alpha I not equal to 0. Here all alpha equal to 0, then only this combination equal to 0. So linearly dependent and linearly independent. Problem wise, you may easily identify all alpha I not equal to 0. At least one alpha I not equal to 0. Here all alpha I equal to 0. Here this look like error. Determine A equal to 0 means linearly dependent. When we arrange the vectors v1, v2 up to vn as a determinant not equal to 0, linearly independent. Equal to 0, linearly dependent. Okay, now these are the important points. Go through each and every one, but then only can easily solve the objective problems. A subset, yes. When we take the subset from the vector space, base is also a subset. Okay, take another subset, S of a vector space that is not linearly dependent is called linearly independent. When we take any subset from the vector space, if it is not linearly dependent, surely it will be a independent. There are two cases only. Then the empty set. The empty set is linearly independent. For linearly dependent sets must be non-empty. Why we say that the empty set is not called a independent set? When we say that dependent, at least we need two elements. When we say this two elements only, one is dependent to other one. Okay, if it is independent means one element is okay and the empty set also is clear. Okay, so empty set is linearly independent, not a linearly dependent. Okay, second, a set consisting of a single non-zero vector is linearly independent. This is from the previous concept only. A set is linearly independent if and only if the representation of 0 as a linear combination of its vector. That is another formation of the statement. As it is alpha 1 v1 plus alpha 2 v2 plus up to what? Alpha n vn equal to 0. The another statement only this one. Okay. Any superset of a linear dependent set, okay, is linearly dependent. Any subset of a linear independent set is linearly independent. Clear? These points will be very helpful when you do the objective problems in this GATE examination. Okay, now let us see some simple problem first. Return the set 1 0 0 0 1 0 0 0 1. These are the standard vectors of this 3 by 3 matrix. Okay, standard basis of R cube. The given set contains 3 vectors. We consider this is what v1, v2, v3. Okay, so I am choosing the scalars from the vector field A, B, C. So what is the linear combination? A into v1 plus b into v2 plus c into v3 equal to what? As per the condition 0. Here 3 vectors only now. So that is 0, 0, 0. Okay. Now multiply here a, 0, 0. B 0, B 0, 0, 0, C. So what is the answer? A equal to 0, first equation. Second, B equal to 0. Third, C equal to 0. So only one chance only. A equal to 0, B equal to 0, C equal to 0. So ultimately, all the scalars are equal to 0. So what is the concept? Linearly independent. At least A not equal to 0, B not equal to 0, C not equal to 0 means we can say that linearly dependent. Okay. Now first condition is clear. Second condition is span. If these 3 vectors alone span this basis, let us check. I am taking any element x comma y comma z. Okay, that vector. See how we can write x comma y comma z. I am taking x into 1 comma 0 comma 0. Okay, then second element 0 comma 1 comma 0, y into 0 comma 1 comma 0. Okay, third z come into 0 comma 0 comma 1. When we operate this one, we can get x y z. So replace x y z by any numbers. We can write like this linear combination. So the elements of this vector span by these vectors only. So that is called basis. See, the basis condition satisfied by first condition linear independent, second span of these vectors. Clear? Okay. Second example. 1, 1, 2, 1, 2, 5, 5, 3, 4 form a basis for R cube. Here I am going to explain in 2 ways. Okay, to understand the concept, how we identify the basis or not. Okay, during the examination, you may find some shortcut method. Let me explain that also. Just try to find out, understand the concept first. Then we will do the problems. Okay, here I am taking 3 vectors. So let us consider v1, v2, v3. Scalars, I am taking alpha 1, alpha 2, alpha 3. That is your choice only. Okay, A, B, C or alpha 1, alpha 2, alpha 3, whatever it is. Here I am taking alpha 1, alpha 2, alpha 3. What is the linear combination? Alpha 1 into first vector, alpha 2 into second vector, alpha 3 into third vector. Its linear combination equal to 0. Okay, let us simplify this equation first. Multiply alpha 1 inside the bracket, alpha 2 inside the bracket, alpha 3 inside the bracket. See, the first problem, when we take this standard basis, standard vectors of the basis, simply we write A equal to B equal to C equal to 0. Here all the elements are non-zero. See here how we are going to form the equation. Okay, alpha 1, 2 into alpha 1, alpha 2, 2 into alpha 2, 5 into alpha 2, plus 5 into alpha 3, 3 into alpha 3, 4 into alpha 3 equal to 0, 0, 0. So totally I am going to form the 3 equations. See, I am taking the first element, alpha 1 plus alpha 2 plus 5 alpha 3. Clear? That is equal to what? 0. Second, alpha 1, 2 alpha 2, 3 alpha 3. See, equal to 0. Third element, 2 alpha 1, 5 alpha 2, 3, 4 alpha 3 equal to 0. See, here I represent one as a vector. Now I write this individual equations. The corresponding equations are first equation, second, third. Now we are going to solve this equation. Okay, there are several methods out there. You know how to solve this simultaneous equation very fast. You have some hints also. Now let us use some matrix form. 1, 1, 5, 1, 2, 3, 2, 5, 4. Taking the coefficients alone, what is the variables alpha 1, alpha 2, alpha 3. Right hand side the constant matrix 0, 0, 0. So first the row echelon form, augmented matrix, matrix first and column constant matrix. Clear? Now by the simplification, taking the pivot element to 1, okay, so R2 minus R1 directly, 1 minus 1 0, 1 minus 2 minus 1 1, 3 minus 5 minus 2, 0 minus 0. Okay, R3, here 2 only known. How this 2 will be coming 0? Here multiplied by 2, then only 2 minus 2 comes 0. So that R3 is changes by R3 minus 2 into R1. So 2 minus 2, 0, 5 minus 2, 3, 4 minus 10, minus 6, 0 minus 2 into 0, 0 only. Okay, again we simplify by R3 minus 3 R2, we can get the third vector goes to 0, 0, 0. Okay, see, note the point, when after applying the element row transformation, will the augmented matrix reduce to some vectors? See, there are 3 rows only, out of 3 rows, complete one row becomes 0. See what happened? By the back substitution method. This is for first row for alpha 1, second row for alpha 2, third row for alpha 3. Alpha 2 minus 2 alpha 3 equal to 0. Here alpha 1 plus alpha 2 plus 5 alpha 3 equal to 0. See, alpha 2 equal to 2 alpha 3. Okay, alpha 2 to alpha 3 means substitute alpha 3 equal to 1. I am taking here alpha 2 equal to 2 alpha 3 except trivial solution, other solutions also valid. See, while I am taking alpha 3 equal to 1, alpha 2 equal to 2. While I am taking alpha 3 equal to 2, alpha 2 equal to 4. So there are non-zero elements also exist. There are infinite number of solutions are there. Okay, so like that, when we know that any one constant equal to non-zero, ultimately we define what? This is what? Linearly dependent. So what is the condition for independent? All alpha I equal to 0. Okay, va? Okay. Now the shortcut method. Suppose during this examination you may not find the time to complete all this task. Better what you do? Take the determinant, write 115, 123, 254. Solve the determinant. When answer comes equal to 0, linearly dependent. Not equal to 0, linearly independent. See, this is the example. So once the third row becomes 0, its determinant comes surely 0. That is what? Linearly dependent. So here I am giving you full explanation. While you write this examination, you use this determinant concept. Okay. Next example, same. In this problem also, I am going to explain this full explanation only, but what you are going to do in examination, put determinant, arrange all the vectors, find out equal to 0, not equal to 0, equal to 0, linearly dependent, not equal to 0, linearly independent. Okay, so there are 3 vectors are given, determine whether it form the basis or not. As usual, we are taking first vector, second vector, third vector, v1, v2, v3, and scalars alpha 1, alpha 2, alpha 3. Here, I am taking this concept from the R. Okay, what is the linear combination? Alpha 1 into v1 plus alpha 2 into v2 plus alpha 3 into v3 equal to 0. The same procedure, I am getting this 3 equation. What are the 3 equation? Alpha 1 minus 3 alpha 2 minus 2 alpha 3 equal to 0 and 3 equation. Okay, when you feel that the procedure is hard, already I told you, use determinant concept, but you should learn the original concept. Okay, right, put the coefficient matrix in this first one and the variable matrix and what? Constant matrix. Then by changing into the row echelon form, augmented matrix here, sorry, the typing error, A comma B. Okay, this is A, this is B. Okay, as usual, the element row transformation, we transform into 1, 3, 1, 0, 0, 1, minus 2, 0, 0, 0, 32, 0. Okay, clearly, by the back substitution method, alpha 1 for alpha 2, alpha 3. So what is the back substitution method? 32 into alpha 3 equal to 0. Okay, once we know that alpha 3 value equal to 0. So what is the previous case? Here substitute alpha 3 value equal to 0. In this case, there is no other choice. Alpha 3 should be equal to 0. Here, alpha 2 minus 0. Here also alpha 2 equal to 0. So here we found alpha 2 equal to 0, alpha 3 equal to 0. Substitute in this case, what is the case? Alpha 1 equal to 0. Okay, so here alpha 1 equal to 0, alpha 2 equal to 0, alpha 3 equal to 0. Totally how many elements, how many scalars we have taken? 3. All the 3 equal to 0. So the vectors are called linearly independent. What is dimension? It consists of 3 vectors. Dimension of R cube equal to 3. The given vectors forms a basis of R cube. Clear? Okay. Second, sometimes in this vector they may fix one unknown value x or a, b, c, whatever it is. You need to find out the unknown value with some condition. What is the condition? Linearly dependent. When you know that the vectors are linearly dependent, when you form the determinant. Why I am using this previous method means sometimes the equal number of vectors may not be given. For example, 3 variables, 3 vectors may be given. Sometimes 2 vectors may be given means the previous method is very useful. Okay, here for 3 by 3 matrix, 3 by 3 determinants are given, 3 vectors are given. So we use this determinant concept for this method. Okay, so determine x so that the vectors in R cube are linearly dependent over R. Okay, so arrange these vectors 1, 2, 0, minus 1, x plus 2, x minus 1, minus 4, minus 8, third. Okay, what is the condition? If it is linearly dependent, determine A equal to 0. Okay, and see here the first row all are non-zero. See the first column 1, 2 and 0. So expanding the determinant by the first column 1 into minus 8x formula minus 4 into x plus 2. Okay, second minus 2 into plus 8 x plus 2 into x minus 1. Third term goes to 0. Okay, so simplifying this one, I am getting x minus 3 into x plus 2 equal to 0. So what is the value of x? X equal to 3 or x equal to minus 2. Clear? So in this way method, determinant concept is very useful. Okay. Second, show that the vectors are linearly dependent. So each and every time we are not applying the original method. In this case, let me show how we use the shortcut method. See, arrange all the vectors in the determinant. 1, 3, 1. Second, 2, minus 2, minus 6. 3, 1, minus 5. Otherwise, see the first row, first vector, second vector, third vector. But always vector should be arranged in the column wise only. Okay, right. Equal to, I am checking that when it is come non-zero or 0. So I am taking from the first row, expanding the determinant by the first row, 1 into 10 minus 6. So minus and minus plus. And minus 2 into minus 15 minus 1 plus 3 into minus 18 formula minus 2, it comes to plus 2. So what is the answer? 16 plus 32, 48, minus 48 equal to 0. So determine A value equal to 0. So the vectors are linearly dependent. As usual procedure, but no need. Already we found linearly dependent. Finally it comes what? Linearly dependent. Because alpha 2 equal to 1, alpha 3 equal to minus 1. Okay. This is the basic examples. A basis of a vector space is, what is the answer? Here I provide the answer also. See, set of linearly independent vectors. A spanning set of vectors. A linearly independent spanning set of vectors. The set containing the zero vector. The set contains zero vectors may be called linearly independent. It may be coincide with the concept little bit. A set of linearly independent vectors that also coincide with the concept. A spanning set of vectors that also little bit coincide with the concept. But which one is absolutely true? Think about that. Not only linearly independent, not only spanning of the vectors. It should be linearly independent that vector spans the vectors. Okay, so C is the correct option. Sometimes when the questions are in this gate examination, you feel that first one is correct or second one is correct. You may think that which one is correct. You may get some confusion. Okay, so try to understand the clear concept, that only you can select the answer correctly. Okay. See, these are the hint points that also will be useful for your examination. If dimension B equal to n, then any linearly independent subset of B can be extended to form a basis of B. Okay, that is finite number of elements in the basis. If dimension of vector field equal to n, the same one, any set of n plus 1 or more vectors are linearly dependent. Okay, if suppose the allotment of vectors are n only, if add any one vector, then the vectors should come what? Linearly dependent. Okay, how it is possible? For example, just let me show you 1, 2, 3. 1, 2, 3, 4. Just adding these two vectors 1, 2, 3, 2, 3, 4, 5, 3, 4, 7 like this. So third vector dependent on first two vectors. So that's why when we add one more vector, then becomes what? Linearly dependent. The set of n minus 1, already n vectors are exist. If you reduce any one vector, cannot span B. For absolutely, if it is linearly independent, all the vectors are needed to form the any vector from the vector field. All I told you know. For example, x comma y comma z equal to what? X into 1 comma 0 0 plus y into 0 comma 1 comma 0 plus z into 0 comma 0 comma 1. Okay, here I am taking any x, y, z from the vector space V. I need the help of all the vectors v1, v2, v3. For example, I want only v1, v2. Can we use v1, v2 alone to form x, y, z of belongs to V? That is not possible. When it is linearly independent, we should take all the n, then only it is span of V. Okay. Okay. I already gave you the answers. For what values of A are the following vectors linearly dependent? Okay. Answer is A equal to -9. How do you prove this answer? See, we can guess this answer. As usual, I am taking the vectors v1, v2, v3. Okay, this is the matrix form of the vectors. Then I follow the determinant value of A. Okay, using this vector expansion, determinant expansion by the first column, because first row all are non-zero. See, first column one element is 0 only now. It is easy to find the determinant value. So that I am taking the first column 1 into the determinant 0, second is 0, third corresponding determinant. What is the answer? -18 minus 13A. See, while this linearly dependent, what is the determinant value? Equal to 0. Okay, so for linear dependent, determinant A value equal to 0. What we have found? 18 plus 2A. Okay, see the second term, 5A minus 2 into 6 equal to 5A plus 12. Simplifying this, we can get 18 plus 2A. For the linear dependence, the determinant of A value equal to 0. So 18 plus 2A equal to 0. 2A equal to -18. A equal to -9. Okay. Simple problem. Determine that the set of vectors linearly independent. Again, I will come to the previous, the main explanation. A, B, C, the constant, V1, V2, 3 are vectors, then form the equations 2A plus 3B plus 8C equal to 0, 6A plus B plus 16C equal to 0, minus 2A plus 2B minus 3C equal to 0. Okay. See the determinant here. I didn't use any row echelon form after that back substitution method to find the answer. I show you that also, and simply I use what? Taking the coefficient matrix and take the determinant. I found this determinant value equal to 0. That's why it is called linearly dependent. Okay. Checking basis in R square. Now I give you some time. Please try to work out this one. Determine whether set 1, 1, 2, 3, 1, 0 forms a basis of R square. If it is R square, we need at least 2 vectors. Here, additionally, we have one more vector, 1, 0. Already I told you, if one more vector is added, see what is the condition. We will check this one. Try to complete. Hope you are doing. Okay. I am taking three constant A, B, C. I consider B1, B2, B3, and the results of the system comes to A plus 2B plus C equal to 0. Second, A plus 3B, C will be cancelled because C into 0 equal to 0. So only 2 equations, A plus 3B equal to 0. Okay, so from this case, A equal to minus 3B. Assuming any value, B equal to 1, we may get A equal to minus 3. Assuming A equal to 1, B equal to 1 by minus 3. Whatever it is, we can find out any value. So here, the constant A, B surely not equal to 0. 0 also is clear, but not equal to 0. So, check this, all this one. The constant surely not, at least any one of the constant not equal to 0. That's why it is called linearly dependent. So do not form a basis of R square. Or I told you, out of these n vectors, if add one vector additionally, it comes what? Linearly dependent. Okay. Please coincide with the hints with this problem. For R square, we expected 2 vectors, but right now we are having one vector additionally. See what is the result? Linearly dependent. Okay. Thank you for watching this video. Surely we will continue this video in future. Extra basis problems and linear dependent and independence with the dimension theorem. Thank you so much.